Swayam Prabha. Digital India. Educated India.
Okay, let's get started with this next session. So this session we'll try to look at what is called as bias variance trade-off in machine learning and try to see why that is important when choosing a good model. And then we'll try to see how you can use regularization as a method for model selection. And finally, if time permits, we'll also see some two different paradigms of supervised learning, what are called as the discriminative and generative paradigms of supervised learning, and see what is the difference between these two. And then we'll conclude that. So let's get started. So we'll try to first do a formal setup of what does it mean to say what is a bias, what is variance, and what is the trade-off that we are talking about. So the setup is as follows. So we'll assume that, so what we want in machine learning is you are given this training data and you are trying to learn a model from this training data, and the model that you're learning, it is not enough if it performs well on your training data alone, but the goal is it should generalize well to unseen data, to the test data as well, right? So that is the goal. So which means, so let's say I give you some training data, and then you build a model out of it, and my test data is totally unrelated to my training data. Then is there any hope for me to learn well? Right? So if my test data has nothing to do with the training data, then there is no way in which whatever model that I learn on the training data is going to perform well on the test data. Right? So there must be a way in which you link your trained data to the test data. Otherwise, there is no way you can do learning, so to say, right? So now the question is, what is a natural way to link your training data to your test data with as few assumptions as possible? You don't want to assume too much about the relation between trained data and test data, but still you want to make sure that the assumptions are as broad as possible, right? So one way which is commonly used is what is called as a probabilistic way of linking your train and test data. And the way we'll do that is by assuming there is a joint probability distribution on the space of X cross Y, right? This is a joint probability distribution. We are not making any assumptions on the form of this distribution or how this distribution exactly looks like, what is the PDF, what is the CDF, none of which we are not making any assumptions on this. So as you know, this is like our instance space or feature space. This is where our features come from, and this is our label space. Right? So in the case of regression that we have been seeing so far, our instance space would be some d-dimensional vectors, and our label space would be just the real numbers, right? So when I say there is a P probability distribution, joint probability distribution, then it means that there is a chance that you are associating with for seeing every point in X and every label being given to X. So one thing that immediately to note here is, so let's say in case of classification, right? So for a moment, let's think of Y as a classification. What would be the label space in that case? So it would just, in a binary classification, let's say, so this would be like 0 or 1, right? So the moment I say there is a probability distribution over X cross Y and the label space is 0, 1, then that also means that this also induces a conditional probability distribution of Y given X, right? So what that also means is that for every given X, for every given feature, there is an inherent chance in the case of binary classification that this feature can be related to, has a label of 0 and it can have a label of 1. For example, a feature like 1, 2, 3, 4. So this is some feature vector in 4 dimension, and the probability of class 1 given this could be 0.8, and the probability of class 0 given this could be 0.2, and so on. So basically, I wanted to wanted you to not miss this, that there is an inherent noise, right? So in the sense that there is no perfect function that maps x to y. So all of this is probabilistic. So of course, if all your probabilities were 1 or 0, then there is a function that maps x to y, but then in general that need not be true. There could be noise, inherent noise in the way the data is generated as well, right? So that's just a small thing. So right now we are going to still focus on regression, where still there is a probability distribution over the labels. In this case, the labels are all real vectors, and so on. So now, how does this probability distribution relate our training set to the test set, right? So there should be some way in which this relates our training set to the test set. So the way we will do that is by assuming that our training data set D, right, which is this, right? Your x1, y1, xm, ym is generated according to P, right? So in fact, PM I should say. So what does that mean? So it means that every x1, y1, so to generate this x1, y1, you look at the probability distribution, and then you draw a sample according to this probability distribution, and you get x1, y1. Now you draw another sample independent of the previous sample, you get x2, y2, and so on, and then you do it m different times, and that is how your data set is generated, right? So this is training. So now what we do in machine learning is you take this data set and put it inside an algorithm, and out comes a model, right? So in the case of linear regression that we thought about, so this model is some h of x, which was some w transpose x, and this is the w that you learnt, which minimized the sum of squares error of this training data. So now you want to see how well this model performs not on the training data, but on the test data, right? So your goal is for this model to perform well on unseen data, in the test data. And how do we do that? Now here is the critical assumption that links your training and test data. So you assume that your test instances are also generated according to P. Right? So it is the same joint distribution from which your test data is also generated. Right? So now, which means there is an underlying process from which both the training and the test data is generated, and you are learning a model on the training data, and you want to see how well it performs on the test data, right? On an average. So that is the goal. So this is how the training and the test are linked. If the training data was from a different distribution and the test data had nothing to do with the training data, the way in which the training data was generated, then it does not make sense to hope for a model which performs well on test data, right? So now here is the link that maps the training and the test data. Okay. So now the question then becomes, right? So now let's put this P of x comma y is still there, and our data set is generated according to PM, which means all our training data is generated. And then I generate a test point, let's say x star comma y star, right? So this is generated according to P, right? So now what I'm asking in the training, in the case of the linear regression model is, what is my expected error of x star y star? If x star y star is generated according to P, what is the expected error of y star minus h of x star squared? Correct? So this is the question that I'm asking. So on an average, right, if I draw a point x star y star from the same distribution which generated the training data, so what is the mean squared error? What is the squared error between y star and the prediction h star? So this h, how was this h learned? So this h model was learnt from where? From D, which is the training, right? And that training also came from the same P, right? So this is what I'm interested in, right? So a good model would minimize this, would have this as slow as possible. Now the question is, there are a couple of things, right? So because of P of x comma y, there is an inherent noise in the model, right? So there is no single y associated with every x. There is a distribution of y, right? So, but then your h is a deterministic function. For every x star, it's going to give a single number, right? So, which means there is an inherent noise that you cannot really avoid in your model. No matter what h it is, it looks like there is some noise because of the p itself that you will not be able to avoid, right? So you have to account for that noise, right? So other than that, what else? So what else could affect it? The other important thing that could affect is how well our modeling assumption on h holds good with respect to the function that relates x to y in our training data, right? So if your h was a linear model, but then your actual y star was generated according to something else, then you still have to suffer some error, right? So I'm giving it, I mean, I'm talking in a vague sense, but then let me actually make this more precise. So now let's make this a bit more precise by saying that our y star is generated as follows, right? So our y star is generated as f of x star plus noise. Okay. So the way that y star is generated is, given an x star, you apply some function f to it and then add some noise. So this noise, let's say, has mean 0 and variance, let's say, sigma squared. This is some noise that is added to our f of x star, and this is what has given us input. So we of course don't know f, right? So we are assuming that the way we are going to model y star is through h. Our guess for f, the form of f is h. It may be correct, it may be completely wrong, right? So now we want to see the relation between how well our assumption on h relates to whatever was the actual f that generated the data, right? So this is what we'll try to exactly make it more formal, in the sense that we will try to look at this particular term and then split this as a sum of 3 different terms. One which will be called as the bias related term, one which will be called as the variance related term, and one which will be called as a noise related term, right? And we'll exactly see how that splitting can happen, right? So, okay, but before that, a slight deviation. So we want one, so to say, a technical lemma. So let z be some random variable, right? So what is the definition of variance of z? So do you know how is variance of z defined? So zi minus z bar, what is z bar? Mean. So zi is a random number, is a random quantity. Z bar is a deterministic quantity, it's a number. Zi minus z bar is also random, but then variance is a number, right? So that should be something else here. And then that's an expectation, right? So your variance of x is just the expectation of z minus expectation of z squared. When you say z bar, it means it's just the expectation of z. It is like, on an average, how much am I deviating from the mean, right? So that is your variance, isn't it, right? So what can we, so if we expand this, what happens? So this becomes the expectation of what? If you expand this, this is z squared plus e of z squared minus 2z e of z, right? So now what happens to this? So can I split this into expectation of 3 different terms? And why is that okay? So expectation is some function, right? So it's like f of a plus b plus c, right? So a is this, b is this, and c is your third term. So why is f of a plus b plus c equal f of a plus f of b plus f of c? That's not true for all f's, right? Linear, right? So expectation is a linear function. It's a linearity of expectation. So you can do that, right? So this becomes expectation of z squared plus expectation of expectation of z squared minus 2 expectation, or rather, okay. I should do expectation of. And what is this? This is expectation of z square, all right. So what is this term? So it's the expectation of z squared. What would that be? Sorry? It is just t of z squared, right? So this is not a random quantity at all. So this is just a deterministic quantity. So there is, if you take the expectation of that, it stays the same. So this is just e of z squared. And what about this? So what are the deterministic terms here? Right? So 2 is a constant. E of z is a deterministic term. There is nothing random about it. So I can take those two outside. So this becomes 2 e of z times e of z, right? So which is just e of z squared. So this guy is just e of z squared minus, and this was what? So this was our variance, right? So what we would need, so let's, the lemma is about e of z squared. It's just equal to variance of z plus e of z whole square. So and this holds true for any random variable, right? So and let's keep this in mind, and we'll see how this is actually useful in a minute, right? So okay, so let's hold this. Okay, so now we'll try to derive the bias variance trade-off as a sum of 3 different terms which are useful for us. So what we wanted to do was we wanted some, okay, so let me actually put down the assumptions clearly. So we are assuming our y star is f of x star plus epsilon, where epsilon has so where variance of epsilon is some sigma squared. Our model says it's a mapping h from x to y. This is what we have learned, and now we want to understand how good is this h on an average on an unseen data point. In other words, we want to see how good, what is the expectation of y star minus h of x star squared, where your x star y star is sampled randomly from the underlying probability distribution from which the data was also generated, right? So this is what we want. So let's try to analyze this term. So what can we do? So let's say we split this as we did earlier. So what happens? So this becomes expectation of what? Y star squared plus h of x star squared x star, right? So small thing to keep in mind here is that what is this expectation over, right? So this expectation is over, so what are the random quantities here, right? So the random quantities, of course, is x star y star, which is a test point that we are generating, right? So that is a random quantity, but that's not all, right? So the h that was learned was also from a random set of m data points that we had initially, right? So this expectation is over all the randomness. It's the random generation of the m training points and the random generation of x star y star. So that is what we are trying to find the average over, and this is what it turns out to be. So let's split this further. So this becomes what? This becomes expectation of y star squared plus expectation of x star squared minus expectation of 2 y star h star. Okay. So what can we say about the expectation of y star squared? So this is like y star is a random quantity, right? So because it's f of x star plus epsilon, where epsilon is random, so y star is also random. So now we are asking, it's like think of this as z. Now you are asking expectation of z squared, right? And we just said in the previous thing that expectation of z squared is variance of z plus expectation of z the whole squared. So this is what we showed. This is a lemma, and we'll actually use this lemma. So if you use that here, what happens? So this becomes variance of y star plus expectation of square. All right? Okay. So what can we do for this? We can do the same thing. Now the z here instead of y star becomes h of x star. Remember, h of x star is also random. It's random because the h was learned from a random set of m different training points. This expectation is over the random set of training points, whereas this expectation is over the randomness in the test point. Right? So because y star is only affected by your test point, and your h of x star is only affected by your training set. Right? So this, but still, you can still talk about this as variance of h of x star plus expectation of h of x star squared minus the 2 comes outside from the expectation 2. So now this becomes expectation of y star h of x star. Now what can be said about this term? How can you simplify this term? First of all, what is this expectation over? What are we averaging over? So this expectation is over the randomness. Where does the randomness in y star come from? From the train or the test? Test. And where does the randomness for the h of x star come from? Train. And these two randomness are completely independent of each other, right? So which means we can kind of say that this is, they're independent. So we can actually write this as a product of separate expectations. We can write this as expectation of y star times expectation of h of x star. Okay. So now how else can we simplify this? What other simplification do you think can be done here? Anything that immediately pops out from this? You're saying you can do? Exactly. So this exactly. There is an a square term, there is a b square term, there is a minus 2ab term, right? So now you can put all these things together. You can just say this is a minus b squared, right? So what does that give us? So the other terms we'll hold on to it. So it's variance of y star, this term, variance of h of x star. Now as she says, this is a squared plus b squared minus 2ab, which is a minus b squared, which gives us what? Okay. So now what we have essentially done is we have taken this error that we cared about on the test set. What is, on an average, what is the test set error that we can hope to achieve? And the goal is to minimize that as much as possible. And we are trying to see if that can be split into more manageable or more interpretable terms. And the way we have, by the derivation, come to a conclusion that it can be split into these 3 terms. Now let's look at each of these 3 terms carefully and see if that makes sense to us, right? So the first term is variance of y star. So what would be the variance of y star? So what is y star? Test. Well, how is y star generated by our assumption? From probability. But in this case, I have made a specific assumption for y star, that y star is f of x star plus epsilon. I don't know what my function is, but I have made an assumption that your y star is f of x star plus epsilon, right? So of course, there is, you can think of it as probability of x comma y also, which is modeled like this, right? So now if this is what y star is, what is variance of y star? 0, which means there is no variance at all. So variance means something is random. So what is random? What is contributing to the randomness of y star? Which term? Is it f of x star or is it epsilon? It is epsilon, right? So the only contribution to the variance should come from epsilon, right? So because f of x star is constant, right? So what is the variance of y star then should exactly be what the variance of epsilon, right? Because you are just adding some extra term to it, and if you subtract it from the mean, that goes away anyway, right? So what is the variance of y star then? Sigma squared, right? So this term is just sigma squared. Now we'll come back to this term in a bit. So this is variance of h of x star, right? So and now how can we simplify this term? Of course, we don't want to expand this out again and then go back to the previous one. So, but the question is, what can we say about expectation of y star? What is expectation of y star? Fx star plus mean of epsilon. So I think I assumed there. So the mean of epsilon is 0. Let's say it's a 0 noise that we are adding, right? So it's like a Gaussian 0 sigma squared, or any noise with 0 with variance sigma squared. We have not made an assumption of Gaussian or normal or anything like that, but let's assume the mean is 0. So then what would be our expectation of y star? So what is expectation of y star? If y star is f of x star plus epsilon, on an average, your epsilon is going to be 0. So then on an average, so E of y star would be what? E of f of x star. But f of x star, what is random in f of x star? It's just a function. So there is nothing random about it. So E of f of x star is just f of x star. So this expectation of y star would then just be f of x star, right? So on an average, you are expecting f of x star to be the answer, but then there is a corruption due to the noise. And the noise has variance sigma squared, right? So this value is just f of x star. Correct? And then this is expectation of h of x squared. Okay, so now, so let me actually write this down again separately and analyze these three terms. So I'm just writing the same thing again. So we have proved that expectation of y star minus h of x star squared equals is the sum of three terms. The first term is sigma squared. The second term is variance of h of x star. The third term is okay. So I can write this as okay. So let me write this way: the expectation of. Tell me if this is okay to write it like this. Squared, right? So this is the expectation of f of x minus e of f of x squared, right? So this is exactly this term basically. So now let's analyze these three terms separately. I mean, so if you just have to give names, so this is called as like the bias squared. This is called as the variance term. And this is what is called as irreducible error. So what we are saying is on an average, the error that the squared error that you would expect on a sample x comma y generated from the test set is the sum of three different terms: an irreducible error term, a variance term, and a term we are going to call as the bias squared, right? So let's analyze these three terms in detail. So first term is the irreducible error term, right? So this is sigma squared. So this term is called as irreducible error term because no matter what model you are trying to learn, right? No matter how good your model is, you will not be able to get rid of this error. This is because there is no single mapping from your x to y in the way the data is generated, right? So your y star is f of x star plus epsilon, and this epsilon is random. So for the same x star, you might get two different y stars. Let's say in your data set, you always had x stars, but then you had for each of these x stars, the label was different. It could be different because you are generating a different y star for x star every time you are sampling from the data, right? So it is like saying that the air pressure, the temperature, precipitation, everything might be the same for the last 10 days, but the amount of rainfall you have got is slightly different with certain variance, right? So that could still happen. So which means no deterministic function can get all the values right? So which means there is going to be some error that you will not be able to reduce at all. So which means your expectation of y star minus h of x star squared cannot be 0. There is an irreducible error component in it, and that is given by the variance. It can be 0 only if your variance is 0, which means there is a function that links x and y in a deterministic fashion. But if you don't assume that, there is an irreducible error component, sigma star, that will always be there. That is the first term. Now let's look at the third term, and then we'll come to the second term. So the third term says, so it is the difference between f of x star and expectation of h of x star squared, right? So the squared is just making it a positive number, so forget the squared for now. So what is that saying? So it is, when will that be small? So that will be small only when your h models f as closely as possible, right? So if your f is like a complicated function, but your h is like a linear function, then you are totally got your model wrong, right? So then you are going to have a high bias. The bias is going to be high. So if you want to lower your bias, you make h as close to f as possible, but you don't know what f is, right? So the only way you can make h as close to f as possible is by making your model more and more complicated, and hoping that your f would be one of these complicated models, right? So which means the more complicated the model becomes, the lower the bias is, right? So the bias of the model kind of keeps going down. So for a linear model, if you are trying to fit a polynomial, that if the true f was a polynomial of degree 10, but then if you are modeling it is using a linear model, then your bias is going to be really high, right? So that is what this term is kind of trying to capture, the bias. So then it begs the question that, so can we then just make the model as complicated as possible and then hope that things will be okay? But then the problem there is, so because of this noise and other things, right? So your complicated model will end up fitting your training data very well, but then the h that you output for an x star will be very, very sensitive to the data set that you are actually seeing, right? So which means if I draw 100 samples now from p of x comma y, and then try to fit an h to it, a complicated h to it, right? So then for a new point x star, your h of x star will be something. Now if I draw a different set of 100 points and then try to fit an h to it, right? So that h of x star will be completely different from the h of x star I got from an earlier training set, right? So which means your model will become extremely sensitive to the training set at hand, right? So which means the variance of the model will become higher. So the more the complicated the model becomes, the variance becomes higher. So for example, if the model was not so complicated, if it was just a linear model and you had certain set of points, let's say, right? You had some complicated set of points and you fit a linear model to it, right? So now if I draw a different set of data points, right? So which might be something else, right? So the linear model will still stay almost the same, right? So it won't change too much. However, if I'm trying to fit a polynomial of the same degree as the number of points that I have, then the polynomial completely changes depending on the data that I have. Is that clear to see? Right? So which means the variance of the model is high if the model becomes more and more complicated. However, the bias is low because you will hope to get a good close representation to F, right? So you'll be closer to F, which means the bias term will be low, but then the variance term will be high for complicated model. On the other hand, for simpler models, you won't vary too much with change of data. Your variance will be low, but then you may be totally off from the truth. So which means your bias might be really high. So now the goal, the hope is to find a balance between these two, right? So this is a trade-off that you cannot hope to ignore. Irrespective of what you do, you are going to have either a high bias, low variance model or a low bias, high variance model. So now this is a trade-off that you have to handle in machine learning because we don't know the underlying truth that generates this, right? So that is what this equation is essentially telling us. So though we did it in a mathematical way and then said our error term is just a sum of these three terms provide excellent intuition to how machine learning algorithm works, right? And what kind of, so if you pick a model, what is it trying to do? Is it a high bias model? Is it a low bias model? High variance model, low variance model? These are the things that one should think about before actually trying to go for a model.